All right. I hope everyone can see me and can also see the presentation.
Yes.
All right. Yeah. So before we begin, just wanted to set the stage for our Dev Day, and that's what this presentation is part of. So the Dev Day, it's a monthly informal event that Sahaj organizes, and it's not something where only say GVs like me talk. We have speakers from other parts of the industry as well. And today, as part of DevDay, I'm going to talk about the history and future of containers. It's something that I am fairly passionate about, which probably brings me to my introduction. I'm PK, also go by Prashant Srivastava, and I'm a tech principal at Sahaj Melbourne. Melbourne, as you would know, is the sports capital of Australia and also home of the NCG. We're not going to talk about sports today, unfortunately, but it is close to midnight here, and hopefully you are having a wonderful evening as well. Um, I have been in the containers and like DevOps world in general for the last I would say around 15 years, and quite a few years of like general programming before that. Um, and we have recently started our operations in Australia, and yeah, and that's the journey I'm part of. So today I will be talking about the history and future of containerization. This is roughly what we're going to talk about. Like we'll try to stick to what's here, but yeah, in case you have any questions, just post them on the chat, and I will come to it eventually, either as we go, or I will probably come to it later if it's relevant then. Um, so we are going to talk about what is a container. First, of course, like if you're going to talk about the history of containers, it's important for us to be on the same page. We are then dive into the history of containers. We are basically going to talk about like some decisions or some projects that kind of like led to the containerized world that we live in nowadays. We will then very briefly look at the present world of containers, and then we will talk about the future of, of containers. I will try to predict the future. I know I will be probably 99% wrong, but well, we can always guess what is going to happen depending on the trends we see in the industry nowadays. All right. So before we dive into this, a show of hands, you can just type in the chat if you want. Like how many of you have used containers before? All right. Clearly a lot of you. And that's not really a surprise, right? I mean, if you look at the world we are living in, and the software development that we are part of, we almost always talk about deploying to containers, or we at least have containers as part of a conversation where when it comes to modern application deployment, right? But let's try to formalize our thoughts, right? We all have used containers, and I guess like we're just so used to it that like we might struggle to exactly define what exactly is a container. So what is a container? Sorry for the obligatory Tupperware image. I guess like that's kind of mandatory if you're doing a talk about containers. Yeah. So my definition of a container is that containerization is an OS level virtualization technique that bundles software and its dependencies in a portable package that can be then used and reused across different platforms. But the key word here is virtualization, right? I mean, this is kind of a very weaseling out kind of a definition, because now I have to explain what virtualization is, right? And let's do that then. What is virtualization? Well, in very simple terms, like virtualization is simply a paradigm or a pattern where the host kernel, which is the operating system kernel, it allows the existence of multiple isolated user space guest instances. We'll look at some of these definitions as we go, like what is user space, what does it mean to be a host, and what does it mean to be a guest. But roughly what this means is that you have one operating system, and and you can have like multiple different operating systems kind of like living on top of it. Now, this is not an accurate definition, and we will come to why. But for the sake of conversation and for a decent understanding, it's a good enough definition. All right. So coming back to what is a container, right? I mean, when we talk about containers, like we think about something that we build into an image, and then we sort of like run it or basically deploy it, right? So it has a limited view of the file system, which means that it carries a file system with it, and you can mount a host file system into it as well. It is also a user space process. This is opposed to something being in kernel space or being a privileged process, which means that you can't really run things that you will not be able to run in a regular user space process, like for example device drivers. Like you will not really see people attempting to write device drivers in a container for a bunch of different reasons. And it's very important to note that, like, because we are talking about user space processes, like the kernel of the container is actually shared with the host operating system. This of course means that it might actually share some of the host vulnerabilities, but like there are again then there are layers between the two. So depending on how the container has been implemented, you may or may not have to concern yourself with this. And of course, very important to note that this is the software level virtualization. You don't have direct access to hardware, and really there's a container engine on top of which the container is running, which is actually the secret sauce. It's basically translating the calls that the host is making. Sorry, the guest is making for the host. Again, we have to understand that this is not an emulation. This is not a hardware level emulation or something like that. This is purely a translation of system calls. So direct system calls are being used. And of course, a container is simply just another process for the host, which means that it is quick to start up. It is very lightweight. This is unlike some other heavyweight virtualization techniques that we will look at later. But it means that because it's very quick to start and it's lightweight, it's also disposable, which means that you don't really you don't really want to fall in love with a single instance of a container. There will be more. You don't have to worry about the instance you have at hand, which kind of like really lends to the immutable infrastructure movement that's been going on through the last couple of years, where you where you talk about we talk about having infrastructure which does not change, you simply replace it. And containers kind of like make it very easy to have something like that. And last, of course, like the reason why we have containers running on hosts is that we are able to run multiple um, containers on a single host, which of course means you can't really give every single container 100% of the memory, 100% of the CPU. So you are able to configure or fine tune the resources that you allocate to a container, right? So that is the definition of what is a container, but well, what is not a container? Sorry, did I go on mute? Okay, sorry. Come back to what is not a container. We just spent quite a bit of time like trying to explain what is a container. It's also important to understand what is not a container, because there are other virtualization techniques out there which will serve kind of the similar function at times, but they're not really containers, right? Not all virtualization techniques are actually containers. And here is kind of a laundry list of things which kind of look similar, but they're not exactly containers. I won't go through each and every one of those, but like I'll just talk about virtual machines, for example. Like virtual machines are like full stack virtualization down to the hardware, which means it has the entire stack, the entire operating system stack, which needs to get initialized, and it has a full fat OS that it needs to when to use containers and when to use VMs. That is the age old question, right? Like when do you want to use containers and when do you want to use virtual machines? Virtual machines are fairly powerful. But it has costs in terms of um, in terms of like startup speed, for example. Plus, it is not as disposable as your regular containers. So if you want quick auto scaling, for example, or if you have very fixed kind of workloads which are not really going to change very often, you can decide to use virtual machine. If you have ever used any cloud service, if you ever provision like an EC2 server, it is a virtual machine, right? So you can do regular stuff that you can do on your computer that you'll be able to do on the virtual machine. And this includes possibly fairly low level hardware stuff as well. Again, there are limits to what you can do on a virtual machine, but you can definitely extract a fair bit of more hardware performance out of a virtual machine than you would be able to do in a container. And security, if you're very paranoid about security, and of course, like containers and container orchestration tools do have layers of security, and in fact, the last couple of years, the container world has spent a lot of effort on making the ecosystem more and more secure. But at a fundamental level, a container still shares the same kernel with the host OS, and virtual machines don't actually do that. So the virtual machine actually has a different host kernel and a different guest kernel, which means that you are more in control of the security if you're an application. Yep. So some of the examples of things which are not containers, jails. Now jails are pretty interesting because they are kind of similar to containers in the sense that they also isolate single processes. Most Linux kernels have inbuilt support for jails, but they don't offer the same kind of flexibility at times. But it doesn't mean that jails are not useful. Jails are very, very prevalent in the sysadmin world, where users or guests to systems are simply provided a quote unquote jail where they can execute their processes. We will talk about jails in a little more detail in the following slides, so I won't really go very deep into that. And there are other examples on this slide. I'll just let you spend a second on this and then move on. I'm basically talking about stuff like virtual kernels, virtual private servers. Like these are fairly esoteric sounding, but they all have some sort of advantage that some people might want to take use of. All right, let's begin our history lesson. I have a big confession to make. I'm not a historian. I am just a regular tech guy, like just like you. So that the dates in there or the events in there, they might not be 100% accurate. These are things that I've told the internet for, and of course the internet has multiple sources of truth. So hopefully these kind of make sense to you, but this is not the gospel. All right. So in the beginning, like before there was anything else, there was chroot. Now, some of you might be familiar with chroot, and chroot is kind of a very low level kind of a technique, but it is still a technique that is widely used in a lot of higher abstracted things like containers, and for a very good reason. So the reason chroot was invented was because someone wanted to test a particular system, like a new system feature in isolation. So they wanted that particular system process to have a different file system root. And to do that, they basically invented chroot, and then it was kind of generally available around 1979. As I said, like you are able to change the root file system for a process. So if you are a rooted process, that is the view of the file system that you have. You don't know what exists outside. One very interesting thing that I really like about chroot is that chroot is also called jail, and it's actually called jail because very famously someone was able to honeypot a hacker and catch them in the act. For those who are not familiar, honeypotting is where you lure a hacker into a system where they kind of like assume they have actually breached the system, but they're actually in an isolated environment where they're not able to make any damage. All right, so this is kind of like roughly what doing chroot looks like. Do you guys want a demo for this? I have a quick demo that I can play around with. It should only take a minute. Right. Bear in mind that I'm on OS X. So I actually have to get into a container to actually play around with a lot of these commands, but let's see how it goes. So we're here. Let's just quickly see what our view of the world is. We are right now in a container, and
Okay, you wanna zoom in a little bit? font
Of
is kind of.
of course, of course. Let me know if you can see it. Is this big enough?
Yeah, it's big enough.
All right. So this is the view of the world for a regular process. It can see that there are so many things in root, and it can play with it as it wants. So let's start jailing. So for that, we will first have to create a jail. So we are just creating a very um, rough kind of a structure for it. A jail will simply be a directory that will be mounted as root for that process. We have to do a few things here, which I'll do to make sure that the jail works. We have to understand that when somebody is in a jail, they are not able to access any other files, which means that if you want things like even ls, you actually have to provide it as part of that jail. So I have to copy the ls bin. I have to copy the dependencies. So this is what roughly the dependencies look like. And for the purposes of this demo, I have at my home prepared this already. So let's also kind of try to run bash in our jail, because that will be nice. Otherwise, we will not have a terminal to play with. And now simply try to run the jail. Now we are in the jail. And how do I know? Let's try to run the command that we did, which was ls-al. Here you go. So all I can see is these three directories that I had created earlier, the bin, lib, and lib64. And that is all that is my view of it. You can also see that my user ID is 0, which means that I don't really like it. It's not really the same as what I had started with. And I can quickly come out of the jail, because this is not a actual jail. I can actually come out. And yeah, just to prove that we're out of the jail. Here we go. So this is kind of like what a jail looks like. Thank you, Georgie. I could have written some loops or some awk, but yeah, it was just easier to just list them out. All right, all right. Yeah, so that is kind of what chroot is like. So clearly, it's fairly basic. All I'm actually doing is just changing the root of the file system. There are of course like some nuances, and I think like until Linux 3.8, like kernel 3.8, it was possible to like run some privileged commands, but I think that has been passed in. So you can run a jail with a little more impunity now. All right, so that was the chroot jail, but that was 1979, right? And now we are what, 2022, I think. Like I think in Australia it is 2022, but we are a little ahead in the time zone. So it took a good like 20-21 years for this technique to sort of like really take a foothold in like general software development. FreeBSD came up with the idea of like chroot on steroids, and here it's kind of very interesting, because it not only emulates the it not only virtualizes the file system, but now it also virtualizes the users, the network, the processes, and it really sort of like popularized the whole. I should not say whole concept, because the concept was there, but it really popularized jails in general. And like around 2000, these things started picking up. this is roughly what it looks like. Again, this runs on FreeBSD, and I don't have a FreeBSD image with me, so I cannot have a demo for this. But let's see. This is roughly what that configuration looks like. Fairly familiar to us if you have used Docker before. But the interesting thing is you can actually virtualize the IP address as well. So the network stack is virtualized. You can see you can mount some devices, and you can have a start and stop command. So fairly more mature than your regular chroot. All right. So guys, like just stop me if I'm not making sense, or if you have any questions. All right, which kind of like has us move on to C groups, or well, container groups. Sorry, control groups, as they are supposed to be called. Like, so this was like the original process container, where like people at Google, I think, came up with this, and now people started kind of like taking the concept of like having group of processes, um, uh, um, sort of like having similar properties, and having like similar levels of virtualization. So C group allowed a more kind of like fine-grained control over allocation of resources. So now you could say that I want to give someone 150 units of CPU, or some process like 300 units of memory, and it also provided namespace for the processes. Now, namespace was not a new concept in 2006, because Linux had introduced namespaces back, I think, around 2002. And namespace, really what it allows you to do is you just like your code that you write in Java or C sharp, right? I mean, it kind of like provides kind of a, lack of a better word, a container for various things. Um, so your process IDs are kind of like namespaced, so that your things inside your C group don't really get affected, or are not aware of things outside their C group. Same with the users, and other things that you can probably think of. But more importantly, it also allowed the prioritization of processes. And we have to understand, C groups is still a very mature thing, and it's still used widely in almost every containerization system. And this is because it allows you to give a container higher or lower priority in terms of scheduling. And even more importantly, it can actually account for the resource usage. So it can actually tell that a process actually used 150 units of CPU, or for this much time, or this much memory. And this kind of like helps you commercialize the thing that you're building as well. And of course, like it also helps you gain a better understanding of how your resources are being used. C groups, unfortunately, I cannot run it inside a container, because for this, like there needs to be a little more support from the host, and I'm running on Mac. So unfortunately, I will not be able to show you this. But if you execute this exact set of commands, I hope it works. But this kind of gives you an idea, right? Like, we are creating two groups of processes, one fast, one slow. The fast one, we are giving 768 units of CPU. The slow one, we are giving, it will work in a VM. Yes. Yeah, this will definitely work in a VM. The problem is that when you are in a container, some of the file system is actually read only, and for C groups, you basically have to create kind of a tree structure in one of the system directories. which is pretty cool, because now you can like control the priority or allocation of resources simply by creating a file or just like redirecting to a file. Yeah, so here you can see like you are basically able to then run both of these processes, and in theory what you should see is the fast one is going to take a lot more CPU than the slow one. And then came the big daddy of it all. This was Docker before there was Docker. Sorry, with -G in one option you have slash, and in the other you don't. Okay. So did somebody find a typo in my?
No. In the previous one, if you see the first two and the last two, the CPU:/fast. Let's say the first line, but the second one has CPU:/fast. Is that supposed to be so?
I think it might be a typo. No, this would actually work. In the first case, I think it points to a directory, if I'm not wrong.
Okay.
And the second one it does not. But I have not been able to run it. I tried this whole evening, and unfortunately, I wasn't able to verify this. But some blogger was able to run this one. I'm hoping it is correct.
Okay, cool.
Sorry about that. Yeah, so LXC was like the first like superhero blockbuster like mainstream container tool. It was Docker before there was Docker, and this kind of like changed the game, because now people started talking about applications in general rather than just very low level processes and things like that. So now you could configure a container, and like if you go back to our original definition of the container, containers are really software with its dependencies bundled together. So now you were able to specify all of that through a configuration. The configuration is still like one can argue it's not as polished as it is for Docker with its Dockerfile and things like that, but it was definitely miles better than where we were back in 2008. So this kind of like set the tone for rest of the rest of the time to come as far as containers are concerned. And LXC was actually pretty much the backbone for early Docker, because the early Docker, I think till like version 0.9 or 1.0, it still relied on LXC for actual virtualization. So this is kind of like what it looks like. We are able to create an image just like you will for like you do in Docker. You can list your images, you can launch images, you can actually copy one image to the other. You can exec into a container. You can list your containers as well, and you can run either in privileged or unprivileged mode. So it kind of like gives you a bit more sense of what are you actually trying to do, rather than so sort of like give privilege access by default like it was in early Docker. I have a demo for this. The good people at LXC actually provide you with. I should have run this before the call, I think. Yep. All right. So they actually provide a tutorial, and it's actually pretty good. Right. I will try to. I will not be able to copy things. All right. Let's just quickly copy some things. Oh, sorry. So the first command failed because this actually supports LXD syntax. So LXD, as my notes say, LXD is the improved UX experience for LXC. So nowadays, most modern LXC deployments. So we don't have any images here. Let's launch an image. Let's bring something. It's pretty fast, so we shouldn't have to wait too long, hopefully. Okay, there you go. And we can actually list the container. So now we have a container running, and you can actually now we are in our container already. So as you can see, like LXC, like the feel of LXC is very similar to Docker, and this is also because the LXC that I'm using now is actually a much more refined version of what it used to be. But you kind of like get an idea that they are fairly similar as far as like basic containers are concerned. Sorry, I have a question. Sorry. I have a question. Since C groups can set a priority for process, does it mean that it interacts with OS processes, schedulers directly? So C groups are actually like the basic support for C groups is part of most distributions. So yes, so C groups, the priority is actually the when you actually run C group, right, and when you're outside in the host, you can actually see that it is just another process that is running as far as the host is concerned. So the priority is actually set at the host, like you would do with a low level command like nice, where you can set the priority of a process. All right, which brings us to Docker, which is something I'm sure a lot of us are already familiar with. So Docker was like the first consumer grade container. I just showed you a demo for LXC, and as I said, it's a bit of a it's a bit of a red herring in terms of how easy it was to do. It wasn't that easy back in the day in 2008, and that was my introduction. That was my introduction to containers. PD has asked, why don't we hear as much about LXC as Docker? Well, I don't have a marketing degree, but I think it has to do do a lot with marketing. LXC was popular, but it wasn't as user friendly. It was still used quite a lot. But Docker came up with a few things which made it very, very attractive. Things like providing a free container registry, for example. Yeah, I'm sure you're right, Denny. Yeah, like it came up with the precursor of Docker Hub, for example. So it was easy to sort of quickly get started with Docker. Docker also made it very easy to write images for containers yourself, because Dockerfile was like just one file. They also introduced things like file system layers, essentially, which made which like I think they did not do it in the first version, but they started caching the layers in the Dockerfile, which meant that it was easier to iterate over as far as writing new images and containers was concerned. And it was so popular that I think within a few years it was valued at $1 billion. And as you would know, a few years ago, I think around 3-4 years, 2019 maybe, it was bought over by a company for a much lower price, because of various reasons that I cannot cover as part of this presentation. But yeah, so Docker was so popular that almost immediately it was adopted by the cloud providers. I think IBM cloud must be uh, must be one of the first. AWS really dove into it. It bundled its EC2 offering with Docker, which I think ultimately now we see ECS, which is the Elastic Compute Service that's there on AWS. So yeah, so Docker was very popular. That is true. So I think Akshay is making a very valid point that LXC was focused more towards the administration side of things, and like things like containers were not looked at as a developer tool, so to speak, and around yeah, I would think like 2008 2010 where when the DevOps movement really took off. LXC was there and people started using it, but it was more of an ops thing than a dev thing back in the day. Docker just made it so easy with its packaging that it just took off. All right, I'm not really planning to give you a demo of Docker because I'm guessing you guys might be familiar with it. But just for the sake of completeness, I will run a Docker image. So I'll just come out of this, and this is kind of like roughly what a very simple Docker container looks like. I'm simply running an image called Ubuntu. I'm running the 18.04 version of it, and it will simply run, right? And I can run any other version, and it's like super quick. Docker, when we say Docker, it's not just running of the image; it's also bundling of the image and things like that as well, which we will come to in the next one. So Docker being popular meant that the other competitors that there were had to sort of like come to a common ground with Docker. I think the number one competitor back then was CoreOS Rocket, and Rocket kind of like Rocket and Docker came together to form the Open Container initiative, or OCI, and that kind of like made sure that that people had a level playing field. Now you could build containerization systems which adhere to OCI specs. Now, when you say OCI spec, as I said, you can either create an image, or and and you can run that image as well. So OCI, I think, has two standards: one for the image, one for the running of it. OCI, I think around 2015 it says, so around 2015 it was donated as open source by Docker, and it came with Runc, which was a reference implementation of OCI, and Runc actually is still going strong, and it is still used by a lot of containerization systems. And this whole initiative kind of like meant that there were a lot of Docker clones that came to be, things like Kubernetes and other such initiatives really got a lot of advantage from these things being open source. Mainly the spec code you can write, but as an industry, when you sort of like agree on common standards, that really helps you to sort of cut through a lot of baggage that you would normally have to. All right. So as containers started becoming more and more prevalent, I think I was trying to Podman kind of, yeah, like Podman is OCI compliant. Podman definitely um, took advantage of the OCI ecosystem. Podman also became popular because a lot of people were not happy with the direction Docker was taking. And again, I can't really cover that as part of this particular um, presentation, but maybe that's a different conversation we can have. Yeah, so as more and more people started creating containers, I think I was trying to find the statistics about like how many containers there are running in the world, and in the last I could find was like from 2019, and there were like 29 billion containers that had been spawned, and since then it must have doubled or even more in the next 3 years, because nowadays containers are even more disposable because of orchestration systems like Kubernetes that came in and totally dominated the market. So, how many of you have heard of Kubernetes or used Kubernetes? Can I have a show of hands? Right, right. So a lot of you, right? And again, that is not surprising either, because like nowadays when you talk about deploying um, either the cloud or the data center, Kubernetes is definitely one of the options that you evaluate as a tech team, right? And Kubernetes is a great project. I think it's one of the crowning achievements for the open source community. Um, I think Google gave it to the world, I think around 2015, and they actually did like something better than actually just um, than just like contributing the software. They actually seeded CNCF, which is Cloud Native Computing Foundation. They actually seeded CNCF with Kubernetes. And for those who are not familiar, CNCF is what is driving a lot of innovation in the container world, or in the like software development world in general for the last 7 years now. CNCF has a lot of backing from a lot of industry leaders, and when I say backing, a lot of it is also financial. So thousands of, well, hundreds, I should say, hundreds of projects and thousands of engineers have come out of out of CNCF, and this single decision by Google to seed CNCF really it really gave a big push in the right direction as far as the container world was uh, concerned, because now they managed to build a complete ecosystem out of Kubernetes. Almost everything is configurable. You can replace one thing with the other. People come up with higher level abstractions. People have come up with commercial products which add new features which are contributed back. So the whole ecosystem right now is kind of so mature that well, you can say fortunately or unfortunately, the innovation just in like pure container world has kind of like been overshadowed by the orchestration world. This may not be a bad thing. Like containers are fairly mature nowadays, but that is where we kind of are at this point of time. Again, like I will not run Kubernetes here, but these are like this is like a simple way you can um, um, deploy something to Kubernetes. Here I'm creating a deployment where I'm saying I'm simply deploying a classic Echo server. Second line, I am getting pods. So pods are basically, for the lack of a better word, they are container instances. So I'm asking Kubernetes to show me the container instances which were deployed with the first line where I created a deployment. And in the next line, I'm simply exposing a port um, from those set of pods, and that ends up um, creating services. So these are very abstracted kind of commands. It's actually doing a lot more than what it shows, but this kind of like goes to show where the container deployment world is at, where the container orchestration world is nowadays. All right, some footnotes. There is a lot of things that I've not mentioned. I've skipped over more things than I've mentioned. But I will just attempt to sort of like just be fair to a few things which are of note. I think I've briefly mentioned in Linux namespaces. This was a very important milestone because it introduced the concept of process isolation in terms of um, not just like process IDs, but things like users and network and things like that. And it was formally added to the kernel in 2002. So I think that was a great thing that is still reaping rewards in the Linux world nowadays. I've briefly mentioned Rocket. So Rocket was launched around the same time as Docker. So there is some impression in some parts of the world that Docker was developed in isolation. It wasn't really. Like there was a movement to sort of get into a more consumer-friendly containerization framework. Rocket was one of them, and it launched around the same time as Docker. And the world came to kind of a full circle. We saw how Docker started with running on LXC, but now we have LXC running OCI containers. So basically now LXC can run Docker. I've not mentioned Mesos, but Mesos is kind of now it's kind of marketed as kind of a data center operating system. And Mesos can do a bunch of different kind of workloads, not just containers. But Mesos also natively supported OCI in 2016, sort of again solidifying the fact that competitors sort of like came to a common ground. CNCF I've already mentioned, and I've also mentioned that right now there are dozens of commercial Kubernetes solutions, commercial and open source Kubernetes implementations that you can use. All right, which brings us to the present. All right, how am I doing on time? Is it all right, guys? All good? I think I don't have a lot of time left. I hope it has been engaging till now, but I might have to rush a bit. So let's get to the current state of the world. And I've deliberately kept it a little light. I'm only going to talk about numbers because we live in the present world. So I think we can kind of like come to an agreement amongst ourselves, talking to our friends in real world about what the world is like. But these numbers, some of them are from Gartner, some of them are from CNCF's annual survey. So right now we can see that 10% of all workloads are containerized. That sounds like a very small number, but we have to understand that this is 10% of all workloads ever in the world. So the world has spent a lot of time writing a lot of software. These are banking, like huge banking software implementations or financial software implementations. There are embedded. So there's embedded software as well. There is a lot of software that runs. I will actually talk about serverless, Nahal. Yeah. So 10% is a significant number if you just consider that containers have only become popular in the last 9 to 10 years. And an average host that run containers nowadays runs 8 containers on it, which is great because this is not just use of resources, but it's also great energy saving as well. And as you know, like this is a time of time for going green, and utilizing the resources to the maximum is the need of the hour for a lot of reasons. But running multiple machines on a single piece of hardware is great. 90% of Kubernetes runs in the cloud now. Now, this is something that's pretty interesting because when Kubernetes came in, like I remember being part of the FUD where people were like, this is the end of like cloud, because people will just like spin up their own cloud now. But as it turns out, 90% of all Kubernetes is actually run by the cloud providers. So these are things like EKS, which is AWS is offering. Then there's Azure Kubernetes service as well. IBM has it as well, and of course the original the OG, which is Google. Google runs a lot of Kubernetes, and Google I did not mention earlier, but Google really accelerated the Kubernetes adoption by actually providing people free tier to run these Kubernetes clusters as part of the Kubernetes tutorial. So it was very easy for a new developer to come in. And this number I found very interesting. Now, to take it with a pinch of salt, because like these numbers are from CNCF. So people who respond to CNCF surveys, they probably are aware of containers and are interested already. So it's kind of a self-selection, but this is a very interesting number. So 96% of tech companies are using or trialing Kubernetes right now. That is like that number is so big that 4% kind of sounds like an error as far as statistics is concerned. So almost everyone, or practically everyone, is using Kubernetes. Now, the keyword here is tech companies. This is not all the companies in the world. It is tech companies. Gartner estimates that around 35% of all organizations are going to use Kubernetes by 2025. So in the next couple of years. So the numbers are going up exponentially. Finally, we come to the part where I get to lie to you, and you guys, like, you cannot hold me accountable because we are all guessing. Of course, like as I said, like predicting the future is easy if you have a time machine. We don't, so we'll just say things, and hopefully some of them come true. So my predictions, my 6 predictions for the next few years. I think there are going to be more containers in more places. So not just in terms of number of containers, but the places where you see containers is going to go up as well. And this is already happening. Point of sales systems in supermarkets, they've already started trialing Kubernetes containers. Edge computing, with the rise of 5G systems, there's a lot more edge computing than it was possible a few years back. There are going to be more stateful loads. Right now, I think only around 10% of workloads in Kubernetes are stateful. Now, by stateful, I mean like this is like persistent data, right? So there will be, I think, a rise in distributed data source like CockroachDB, YugabyDB, where people will start trusting the orchestration system to orchestrate their data in a way. There is going to be a lot more serverless out there. I think most of the cloud providers have already started like using Kubernetes for serverless in one shape or the other, but frameworks like KEDA are already pretty mature, and they enable you to have event-based workloads. I think there's going to be a lot more cross cloud. Now we have been hearing about having hybrid and multi-cloud workloads. Now people do that because you want high availability. You also want to reduce costs. You want best of the breed kind of a thing. So with that, there is definitely going to be more workloads which are going to be across multiple clusters. And there's already a lot of work that's being done in this space. There's Crossplane, there's DKP. People also consider things like Pulumi to sort of like help people go cross cloud. There are going to be a lot more AI and ML workloads now. I mentioned that you don't want to do a lot of low level hardware stuff. And that has been sort of like one of the Achilles heel for containers. But I think there is better like GPU integration that is happening. It is almost there, but it's not as mature as CPU or memory provisioning. So I think there's going to be a big tick in the AI ML workloads in the coming world. I don't mean like your regular run a few numbers kind of a thing, but there are AI algorithms out there that probably need to use the GPU a lot more. Then I think I am also predicting the death of the container. First, let's have a bit of controversial opinion. The rise of the anti-container. I think with systems like or the platforms like WebAssembly, which lets you write cross-platform binaries or binaries that can run in a cross-platform runtime. I think it is going to take more traction, and as it becomes more easy, there is more orchestration around it. If it is something that really works better than regular containers, I think it is going to have good adoption. And that actually brings me to the end of this presentation. Thank you for being here. Thank you for bearing with me. If you have any questions, I can take a few questions for the next few minutes. If we don't have any questions, I think we can stop. I'll just I'll ask one of the moderators to sort of drive it from here.
Yep. Thank you, PK. Thank you for your time.
Yes.
Thank you, folks, for joining. I hope this kind of a presentation discussion was helpful. If you have any feedback, if you have any suggestions, please you can drop a message on the Meetup page under the DevDay. In case if you have any kind of an ideas or experiences that you would like to share with us over this DevDay platform, even you can reach out to us using the Meetup.
All right. Yep. So here's bye from Australia. Good night. Thank you.
Thank you.